Hi everybody, welcome to 9.3. As promised, this one will be much shorter for you. Let's investigate some special parallelograms. Here's all of the quadrilaterals organized in a really fancy Venn diagram. What I want you to notice right here is that quadrilaterals is the bigger box all the way on the outside, and inside live all the quadrilaterals we could possibly draw. What I should have included in here was also just a kind of random quadrilateral that is neither a kite nor a parallelogram nor a rhombus nor a square, and all of the quadrilaterals that would otherwise fit no other categorization, just be random kind of quadrilateral. But here we have kites, which have a very specific definition we'll get into a little bit later, but two pairs of adjacent and congruent sides, not opposite, but adjacent sides are congruent, literally looks like a kite. We've got trapezoids with parallel bases, and specifically isosceles trapezoids with parallel bases but congruent legs. Here's where we're going to be focusing today, though. Inside the parallelograms group, where we've already defined parallelograms as opposite pairs of parallel sides, we're going to look a little bit closer at rectangles, squares, and rhombuses. Notice that the blue and the pink overlap. Inside the blue is all of the rectangles, which are defined by equiangular quadrilateral, rhombuses, which are an equilateral quadrilateral, and where they overlap, it is equiangular as well as equilateral, and we get what we commonly know as a square. Notice that in none of these do I have the parallel sides marked, because simply having the equal angles or the equal sides is enough to force it to also be a parallelogram, so we do not need that additional information. This is all we need to know that this is a rectangle. That's the essential defining characteristic of each. I'm going to have you guys now investigate these shapes on some little applets I'm going to give you in a moment. When investigating their properties, we want to think about all of these things here. We want to compare opposite sides and think about if they're parallel or if they're congruent. We know that they will be because they're all parallelograms, so they will be parallel and congruent. Opposite angles, we've already investigated that. We know that parallelograms have congruent opposite angles. They are not supplementary for parallelograms. Consecutive angles, again, all parallelograms we know have supplementary consecutive angles. They're not congruent. But we're going to start investigating diagonals a little bit closer today, and this is what I really want you to focus on and think about is the diagonals. You'll notice some stuff with the angles as well, though. Think about the diagonals. Are they congruent? Are they perpendicular? Is one or both of them bisected? Do they bisect the angles, the opposite angles that we were talking about? So I'm going to give you those three applets. I want you to explore and use your findings in your exploration to go ahead and complete your properties chart that, or no, well, no, you're not going to complete it, but you're going to do 3 more columns, the properties chart that you did in 9.2b, and you're going to submit that to 9.3b. Let me show you a little bit about the applets real quick. Here are the applets that you're going to work with. There's some buttons on the right, and you can click and drag some vertices, so we can kind of move this rectangle around with A or B. D can make it bigger or smaller, but look what happens when you click these boxes on the right. I can choose to show the diagonals, and it also shows me lots of measurements. As I continue to move this around, I can see that the top and the bottom of the rectangle remain congruent. The left and the right of the rectangle remain congruent. We know this about rectangles, but I can also show angles, and I can investigate the lengths of the diagonals. The other boxes that are here are to show half of the shape shaded in as a rectangle, and I can use the reflection to show that there's not symmetry here. These two triangles are congruent, but this is not a line of symmetry. Same thing happens the other way. The rhombus template, very similar, but there's an extra button. When I show diagonals, I get the same thing with some measurements, and you can investigate what happens with diagonals as I move this rhombus around. I can show the angles where the diagonals meet the vertices, but I can also show the angle where the diagonals intersect. Please continue to drag everything around. Again, I can highlight triangles. In this case, I do see symmetry. And then lastly, with the square, you can go ahead and click all the same stuff. Okay, some examples of how we can use all of those different properties that you found. So I've got quite a few here. I'm going to start in the top left. I see that I'm given some information that ABCD is indeed a parallelogram, and I'm told that the perimeter of the whole shape is 46 units, which means all the lengths all the way around equal 46. I'm being asked to find lengths AB and BC. I'm given some expressions for a couple of those lengths, and I know that parallelograms have opposite sides that are congruent, so I can fill in a little bit of missing information here, even though it's still in the form of an expression. All four of those sides, because I'm told the perimeter, can add up to 46. So I'm going to go ahead and write an equation where I've got 2x minus 7 times 2, because there's 2 of them, plus x plus 9 times 2, because there's 2 of those sides, is all going to add up to 46. Just a little bit of quick algebra to do here. I'm going to make sure to distribute these 2's inside each of those. I'm going to get 4x minus 14, 2x plus 18. Now I'm going to go ahead and make sure that I collect my like terms. I get 6x, negative 14, and 18 gets me a positive 4. Go ahead and subtract 4 from both sides. And lastly, I'm going to go ahead and divide by 6. And I find out that x equals 7. I'm not done yet. They asked me to find the length of AB. So I need to plug in the x equals 7 that I found to find out that AB equals 16. And on BC, I'm going to do 2 times 7 minus 7. That's 14 minus 7, and I get that BC equals 7. On the right, I see the markings for a parallelogram. I don't see anything marked congruent, and I don't see any right angles, so I don't think we have a rectangle or a rhombus here. I do see some angles there that I'm going to go ahead and try to investigate a little bit further. So I'm trying to get my eraser going. There we go. So the angle that I see here is 57, and I know that opposite angles are congruent, so I could fill this in. Not sure if I'm going to need that. I see 64 and y right here. Well, I'm not entirely sure what y would be quite yet, but I do know that in a parallelogram, I have alternate interior angles, so I know that this is 64 degrees, and now I can use that to figure out what y equals, because 64 plus 57 plus y all needs to add up to 180 degrees inside of that triangle. So let's see, I've got 110, 121 plus y, and that means that y equals 59 degrees. Alternatively, I could have remembered that consecutive angles are supplementary, so I know that that entire angle V right now, the measurement of angle V equals 180 degrees minus 57, which is going to get me 123. So if all of this is 123 degrees, then I can go ahead and say that y equals 123 minus 64, and I'm going to get 59 degrees the same way. Okay. Down on the bottom, let's see. I see congruence markings right there, so I know that this is at least a rhombus, potentially a square, because we are equilateral. How can I determine that this is indeed actually a square? Because I have that right angle marked right there. Consecutive angles are supplementary and opposite angles are congruent, so this is enough to know that this is a square with only that one angle being marked. Since I know this is a square, let's see what we can figure out here. I'm told that this segment right here is 17, and I'm asked to find x. In a square, the diagonals are perfectly bisected and congruent to each other, and I know that the central angle at the diagonals right here is a right angle, and that this is 45 degrees. I have a 45, 45, 90 isosceles triangle right here. That's enough for me to find x. I can remember my pattern of a square root of 2, or you can use the Pythagorean theorem if you can't remember. But we have 17 square root of 2 equals x right here. My units are here, so I don't need to include it in my answer. I'm just finding the variable that plugs in, and it's already got units on it. Bottom right, again, I see some markings to know that this is a rhombus, potentially a square, but nah. I see 60 degrees in the corner right here, so it's not sitting straight upright, and so it's not perpendicular sides. This is not a square, this is just a standard rhombus. But I'm now being asked to find this angle, so how the heck am I going to do that? Okay, well, just in the previous example up above, we know that opposite angles are congruent, and I know that this whole angle is going to be supplementary, but how does that necessarily help me find that missing angle? I don't know how that 120 breaks up. Do I? If you remember from your properties, we should have written down that diagonals in a rhombus bisect the angles. So if that's 120 degrees, this is indeed broken up into 60 and 60. We actually have two equilateral triangles right here, but my question mark angle is 60 degrees. Okay, a few more examples and then we'll be all wrapped up. Each diagram here is drawn so that it looks like a square, but we're being told that it does indeed represent a parallelogram, but we're not sure if it can be further classified as a square, rhombus, or rectangle. Remember, we can't trust just how a diagram looks. We need to see specific markings. Because even if it looks like this is 90 degrees, maybe it's 89.9 degrees and we just can't visually perceive the difference, but that would make it not a square. So let's look at the information that we see here to see if I can determine any further exactly what's going on. In this diagram right here, I'm told that I have 3 centimeters and 5 centimeters. So at a minimum, we know that this is not a rhombus or a square. It might be a rectangle though, if I can determine that the angles are 90 degrees, or that it for sure meets one of the other properties that's unique to a rectangle. So look at what I see here. I notice that this angle and this angle are marked congruent. I see a lot of AIA angles. So this angle and this angle right here is definitely confirming that the top and bottom are parallel, but we already knew that. More interesting is the fact that these angles here are congruent, making this an isosceles triangle. And then right here, this angle and this angle are congruent, making this an isosceles triangle. So what I wind up with are two congruent and bisected diagonals. We know that the diagonals are always going to be bisected in a parallelogram, but they're congruent specifically only in a rectangle. So I know that this is definitely a rectangle. Moving over to the example on the right, here I can only see that the top and bottom sides of this are congruent. I'm not sure about the sides, but I do see this right angle in the middle. Looking at your properties, the only shapes that have perpendicular diagonals are rhombuses and squares. I don't know if this is a square because I'm not sure if this is a perfectly perpendicular set of sides, but I can definitely say that this is at least a rhombus. And maybe it's also a square, but we don't have enough information. Moving to the next diagram on the right, I again see those perpendicular diagonals, which means again, it's a rhombus or a square. But with this additional information of 45 degrees right there, that means that indeed, because these are all congruent triangles, I do have 90 degrees in the corner, and this is a square. Down in the lower right, I see 5, 5, 5, and 5. Again, we have at least a rhombus, and the question is this also a square? But we can see that we have definitely not congruent diagonals right here. One of the diagonals is longer than the other diagonal, and that happens when the rhombus leans over because it's longer this distance from those two far corners pinched away from each other, these two that are being moved closer to each other. So this is a rhombus and decidedly not a square. In the middle right here, I'm seeing 3, 3, and 3. I'm seeing some equilateral triangles right here, which is telling me that this is 60 degrees. I've got a lot of 60 degrees right here. And I'm seeing 3 and 3 on the right and left. So what can be happening on the top and bottom? Well, I know that this is a straight line, so this has to be 120 degrees. Okay, I've got some congruent diagonals for sure because each one totals 6, but they are definitely not perpendicular. That means that we're looking at a rectangle right here. Congruent, but not perpendicular. We've got a rectangle. On the right, I have congruent diagonals and congruent sides all the way around. So it's a rectangle because of the congruent diagonals. It's a rhombus because of the congruent sides. And what do we get when we have a rectangle and a rhombus? We know that this is a square. All right, guys, that's enough for today. Please make sure you submit your continued properties chart to 9.3b. If you've made some revisions after I walked you through those examples, go ahead and resubmit. That's fine. I'll leave you some feedback and we'll review all of these properties in class. I just want to make sure that it looks thoughtful and not just randomly completed. Thank you.